So good morning. Welcome to the first session of the day. And so I welcome the first speaker. The first paper is Learning Where and When to Reason in Neural-Symbolic Inference. So I'll leave you the stage.
So hello, I'm Christina. And so we'll talk in the 20 minutes or so about our work that is basically a method how to incorporate constraints in neural networks. And it was done in a collaboration with my colleagues at Samsung AI. And we recently published and presented this work at ICLR this year. Okay, so a little bit of motivation, like why we're doing this. We started to look at the state of the art and to see how people incorporate constraints into neural network or more in general machine learning models. And we noticed that this is usually done in a soft way, so where the constraints are enforced mostly at training time, while they are not satisfied by all the predictions. So our goal was to create like a method that also impose hard constraints. So we want all the prediction to respect the constraints or the rules we want to impose. So the idea we had was to have this neuro-symbolic integration method that is based on three main components. So the idea is very simple. We have the first component, what we call the neuro-solver, that basically take a problem and try to solve it. So this is a neural network or machine learning method and try to solve a problem. But of course, since we cannot have accuracy of 100%, the prediction might have some errors that they don't satisfy the constraints that we want to impose. So then we apply a second network, which is the mass predictor. The mass predictor has the role to identify the errors in the prediction. And then we correct the errors with a standard symbolic solver. So, and why we are not doing directly a symbolic solver is because in many real-world scenarios, this is not computationally feasible. And so we kind of use this second network, the mass predictor, to redirect the focus of the reasoning. So we don't want to reason exactly on everything, but we want to use a neural network to approximate the solution first in a fast way. So the neural network will solve the easy part of the problem, and then we leave just the hard part of the problem for actual reasoner. Okay, so this is just a high-level schematic of the system we have. That is called NASR, that stands for Neural Attention for Symbolic Reasoning. And as you can see, first, we provide the input to the first network, the neurosolver, that solves the task. This will give us in output a symbolic solution, so a vector, and this vector might have some errors that violate the rules. So then the mass predictor will output another vector, taking in input the solution, and this is the masking vector. So this masking vector identifies the errors and can be done like, for example, with standard masking, you have 0 ones. So 0 are the errors and 1 are the correct part of the solution. So then we combine these two vectors with an adapter function. So the adapter function kind of deletes the error from the symbolic solution and format the solution in a way that is the format is appropriate for the symbolic solver that we are using. And the symbolic solver then with the rules will output the final solution. So there are three main properties that are kind of interesting for the system. So the first one is that we can use any kind of constraints. So we're not restricting to logic constraints. Constraint could be also a differential equation for a mechanical system or any sort of constraints. The second one is that the neurosolver, so the first, what I call network that want to solve the task, it doesn't have to be a neural network. It can be any machine learning method. It can be even a black box. And the last one is that this method can be reduced to only neural or only symbolic, depending on the behavior of the mass predictor. Because if the mass predictor does not identify any errors, then the final solution would be basically what we created with the Neural-Solver, so with the first network. While if the mask predictor masks everything, then everything will be solved by the symbolic solver. So in the reality, what happened is that we are in between these two extreme cases. So the mask predictor allows the first network to solve like most of the problem, so we can solve it in a fast way, and then the symbolic solver just fix the hardest component of the predictions. Okay, so what we are actually learning is this function here, which is our hypothesis function, which maps an element in X, where X is the set of all possible inputs to the task under consideration, to a probability distribution over Y, which is the set of all possible complete solutions. So first, we apply the Neural-Solver. So the Neural-Solver has the same input and output spaces as the hypothesis function. And then we apply the mask predictor. So the mask predictor takes in input a probability distribution over the solutions, the complete solution, so over Y, and produce an output, a probability distribution over Z. So Z is the masking space, which like in standard machine learning is usually 0 and 1s. So 0 is the masked element and 1 is the component that you want to keep. But can be also different things depending on the symbolic solver that we are using. Okay, so then we combine these two, like the output of the Neural-Solver with the output of the mask predictor using an adapter function that, for example, if you use 0 and 1s, like in standard machine learning, we can use the element-wise product. So we have, if you think about like a vector with all the prediction and then a vector with the masking elements, you just multiply them and then you kind of delete the errors and substitute them with a 0. And then the symbolic solver kind of fills the gap, so change the zeros to like a feasible solution that satisfy the constraints. And the symbolic solver, of course, takes in input also the rules that are the constraints we want to impose. And it's important to notice that if the mask predictor does not have false positive, then we can ensure that the constraints are satisfied at test time. Okay. So, and how do we do the learning? So first, we have two kind of versions. So the first one is that we use supervised learning to train the components in our system. So both the Neural-Solver and the mask predictor are trained with the supervised learning. And then we put together all these components, so the Neural-Solver, the mask predictor, and the symbolic solver, and we just run this whole sort of pipeline all together. And this is the first version of NASR. And then the second version is once we put everything together, we can refine it and fine-tune it with reinforcement learning, bringing also the symbolic reasoner into the loop. And another thing is that when we use reinforcement learning, we can also decide if to fine-tune both components, the Neural-Solver and the mask predictor, or just one of the two. In the case we have the Neural-Solver that is a black box, then we want to fine-tune only the mask predictor. And in the case the Neural-Solver is a neural network, then we can do the whole thing. And for reinforcement learning, we use a very basic version of like loss function. There's the one that you see here. Okay. Let's go to experiments. So the first experiment we did was for the visual Sudoku task. So the visual Sudoku, we have an input and an image, so a picture of a Sudoku board, where we have, of course, some hint cells, where we have the numbers, and then the empty cell that we want to fill. And the goal is to fill the whole board, of course, with the rules of Sudoku. So in this case, the pipeline is a little bit more complicated. So the Neural-Solver, we decompose it in two components. So the first one is a perception module that translates the picture to a symbolic vector. So you can see here we have a 7, 8, then a blank, then 4. And here we have a vector like this. Of course, it's not really a vector, it's just a probability distribution over all possible vectors. Then we take this in input for the second network of the neural solver, which is the network that will actually perform, find the solution of the Sudoku. So we have the first network just read the image, the second network compute the solution. And once we have the solution vector, we give this in input to the mask predictor, which will output a masking vector, in this case with 0 and 1s. And we can see that, for example, in this solution, we have a 7 here and a 7 here. And this violates the rule, because then we have a 7 here. That means we have 2 7 in the same row and also in the same block. So it violates 2 rules. And then with the adapter function, we just apply the masking vector to the solution vector. And this is given to a logic solver with the rules will output the correct solution. So fixing the errors. And implementation-wise, for the perception part, we use just a simple CNN for NIST digit recognition. And the solver NN, which is the second network, and the mask predictor, we use just transformer models. And for the symbolic solver, we use Python version of Prolog. I don't know if you know this library. And we also have like a brute force backtracking based algorithm. I will say later why. Okay. So for the visual Sudoku task, we use 4 different data sets. Each of them, they have different challenges. The first one is a big Kaggle, is the biggest data set and has the problem of scaling for the reasoning component. The second one is called minimal. So this one is the one that has only 17 hints, which is the minimal number for a Sudoku to provide a unique solution. Then we have a data set that has, each board has multiple solutions, and then we have this last data set because it was used by some state-of-the-art method. Okay, and then we compare our system, the version without RL and the version with RL, against a symbolic baseline. So the symbolic baseline, what we do, we take the images, we translate them into a symbolic vector, and then we just run a symbolic solver directly from that. And then we compare also with Neurasp, which is a Neural-Symbolic method that combines ASP programs with neural networks, and then with the SATnet, which is kind of Neural-Symbolic method that use some relaxation of logic. And the last one, which is also important, is we combine SATnet with our system. So we use SATnet, this existing method, as the role of neurosolver in our system, and then we see what happened to the performance. Okay, these are the basic results on the data sets, and we can see that first we outperform the baseline, or we perform the same in some cases. In the case that we perform the same, like in the minimal 17, which is the hardest data set we have, for example, you can see that we perform the same as the symbolic baseline. But even in this case, our method is to be preferred, and I will talk a little bit later about this, because we are more robust to noise, and also we are more efficient than the symbolic baseline. And then the other thing to notice is that when we incorporate an existing method like SATnet in our system, we can see that we can have a boost in performance. For example, if you look at their own data, so the data they use in their paper, we can go from a 60%, but integrating in our system, we reach up to 81%, which is kind of like a pretty important improvement. Okay, so now we'll talk about 3 analyses we did on this data set. The first one is about the efficiency. So we wanted to understand how much, like the trade-off between the performance and the computational time for our system and the system we compared with. And we can see that we are on the Pareto front comparing these two metrics. And we are also the system that are closer to the optimization objective, which would be like 0 computational time and perfect performance. For other systems, like the symbolic baseline, we can see that the performance is quite good, but then the computational time is a little bit bigger. Or other systems like SatNet, we are very fast, but then the performance, we have a drop in performance. And the second analysis on the right is that we wanted to see what happens if we limit the computational time, like how the performance behave if we limit the computational time. And we can see that all the neural-based approach are very fast to reach the peak performance, while the symbolic baseline catch up a little bit later on. So we can see that even if in the data set in which the performance is the same, we have this kind of delay for the purely symbolic methods. Okay, so the second analysis we did was about the robustness to noise. So we said, okay, what happens if we inject noise into the data sets? So the first type of noise we considered was the rotation of digits. So we rotate the digit in the Sudoku picture from 0 to 45 degrees. And we can see that, so our pipeline is the blue and the green lines. So the blue is without RL and the green is with RL. And we can see that we are, especially with the one without RL, we are much more robust to noise. If you consider like a rotation of, I don't know, 25 degrees, the symbolic baseline drop the performance to around 20%, while our method is still around 40. So to double the performance, and even though they started more or less with the same performance, actually the symbolic baseline was slightly better than the version of our system without reinforcement learning. We don't observe the same property for the reinforcement learning. I mean, it's still robust to noise, but slightly less. But we have a gain in performance. So this gap, you can see, is still a little bit bigger, but it's not that evident, let's say. And so the second experiment was to adding Gaussian blur to the digits. And also here we obtained basically the same results. Okay, so and the last analysis we did is we look at the attention maps in the transformer, because if you remember, both the neuro solver and the mass predictor, they are both transformers, so attention-based methods. And we look at the attention maps to see if they're actually learning something or it's just like some overfitting on the data set. But we can see that if you consider like one cell in particular, then we can see that the transformer look at the row, the column, and the block. And this holds both for the neural solver and the mass predictor, even though for the mass predictor it's not that evident as the neural solver. It's a little bit more like noise around, but we can see they're actually learning the Sudoku rules. Okay. The second experiment that we did was for scene graph prediction. So here the task is given an image, like a picture, we have, and we have in input also some bounding boxes with the labels for all the objects that are in the picture. For example, here we have hat, person, jacket, horse, right? So the goal is to create a graph, and the graph will have one node per object in the image, and then the edges between the nodes are the predicate that is between, so the relation between two objects in the image. Okay, so then what we use an ontology that only has domain and range for all the predicates in the data set. For example, we have the domain where is person. So in this, we want to apply this because we want to avoid some errors like a shirt is wearing a person instead of person wearing a shirt, and type of errors like that. And and we can see here on the right that the pipeline works as in the case of the visual Sudoku task. So we have that first the neural solver produces a solution, then the mask predictor identifies the errors, and the symbolic solver corrects the error. So, of course, this is a very, very simple ontology, just domain and range. But if you can also use more complicated ontologies, considering, for example, symmetries or other properties of the relations. As a data set, we use the GQA data set. So this data set is basically a balanced version of visual genome. I don't know if you're familiar with this data set, but it's just a collection of images with the bounding boxes and the labels and the scene graph output for each images. Okay, so this is the main results for the scene graph prediction. I'll explain this table a little bit. So we performed 2 experiments. One is all shot and one is zero shot. So for zero shot, the difference is that at test time, we only see triples we never saw before. So we didn't see this triple in the training time, but only at test time. While for all shot, you can also, like, it is both of these cases. Like, you could have seen or not seen the triple before. And first, we compute the accuracy of a baseline model. So this baseline model is basically the neural solver part. So we just take an image with the bounding boxes and output a scene graph. And this scene graph might have some errors. So this is our baseline, and is a message passing based architecture. Then we compute the max improvement given by a probabilistic symbolic baseline. So this one, what we did is we take an input, the scene graph, and we just run a probabilistic solver to find the most probable scene graph. And this, we were able to run it, but it takes days because the data set is quite big. But this gives us an upper bound of the performance that we can reach with this simple ontology. Of course, if we consider a more complicated ontology, this probably will be much higher. And this we can reach up to 2% of improvement with this simple ontology. And what we wanted to see is if we use an ASR instead of the full probabilistic symbolic solver, how much of this improvement we can obtain. And we can see that with an ASR, we are able to recover basically the whole thing, so almost 100% everywhere, even on the zero-shot triples. And this is quite good. And yes, that's it. Okay, so this concludes my talk. And please come to the poster later after the coffee break, also because I'm looking for collaboration. So if you want, you can talk to me or send me an email. And we have also the code on GitHub if you want to try it. And that's it. Thank you.
So are there any questions?
Yeah, so when you, when you adapt the cases, like, you know, when you take the mask prediction and then you adapt the that prediction using the symbolic solver, does your symbolic solver like just search the search space from the like detected errors, or do you have like special rules for like seeing the difference between the two, the expected solution?
Yeah, I just take an input. Let me go back to that slide. So I just take an input the combined version, so I don't see these 2 single components. I just have a.
Right, but when you want to correct the masked solution, do you have like special rules for doing that, or how do you?
For in the symbolic component?
Yeah, when you feed it to the logic solver.
So exactly. So for the Sudoku solver, I just have the Sudoku rules, and I run sort of like a prologue program with the rules, and then it's just standard.
Okay. All right. Thank you.
I don't know if I answered.
Yeah, I have an idea, but I'll tell you during your poster. So, okay. Thanks.
Concerning the scene graph prediction. What is not very clear to me is whether is it possible in case in which one of the labels which are attached to, for example, this picture are wrong, if you can somehow recover. It's not clear to me what is the relationship between the learning process which takes place when you extract these labels and the corresponding subsequent process. I mean, there is a sort of connection between these two computational mechanisms, or they are just separate. I meant you have labels which are extracted, and later on you have a process which relies on the labels but doesn't have any subsequent potential modification of the label, because you know, this picture in most cases is wrong, right? In computer vision you may have a lot of mistakes and a lot of, you know, it's not reliable, right? So the bounding box, especially in a picture like this, may have remarkable you know, errors. So what is the actual interplay between the sub-symbolic part and the scene graph prediction?
Yeah, so like in this task we consider predicate classification. So for scene graph prediction there are also other tasks. So predicate classification, we have like in the system you have an input already, the bounding boxes and the labels. So it's not something you have to infer. Right? But to answer your question, these two parts are first trained separate, completely independent. So you have this neural network that produce the, but then if you use reinforcement learning, these two parts are kind of merged together. So the first network will have in input the signal, the reward signal from the symbolic solver. Maybe I can have some additional slides to show you that, maybe. Exactly. So you have, if you have some, like you have some signal from the symbolic solver, right? So you say, okay, this triple is wrong. Then this will also go back with reinforcement learning and kind of modify a little bit the weights in these two networks. And you can also decide if just to modify the weights here or also only here. But in this case, it's kind of like integrated with reinforcement learning.
Thank you. I guess we have time probably for one more question. I don't know.
Okay. So is it reasonable to think of the mask predictor as an attention mechanism for focusing the attention of the symbolic solver in the places where it can add most value?
Yeah, exactly.
But is there some kind of replication between what the mask predictor knows and what the sub-symbolic solver can do? Because if the mask predictor can determine what's correct and not correct, then it's, in some sense, it's replicating what the symbolic solver does?
Yeah, so the point is that the mask predictor has an easier task than the solver, because the solver has to learn how to also produce the solutions, while the mask predictor is more like consistency checking. So it's a much simpler problem. This is why we kind of separate the two.
Verification.
Exactly, a sort of verification, and then so this is why it's able to learn something, because we also did some ablation studies in which instead of the mask predictor we just considered the confidence of the neural solver. So we said, okay, every triple, like in this case of scene graph, every triples that has a higher confidence, like we select a parameter, I don't know, 0.8%, so 0.8. Everything that is higher, we just keep it, and the rest we drop, and then we run the symbolic solver on the lower part, like the part we dropped, and we see that we cannot reach the same performance as using the mask predictor. So the mask predictor is actually learning the rules and learning how to do consistency check and verification. Yeah.
Maybe one last question.
Hi. I was curious. Oh, two quick questions, if I'm allowed. Well, the first is, have you tried, and I assume it's capable if the symbolic solver is differentiable, to train it end-to-end? And the second question is, for training the mask predictor, you mentioned that it's pre-trained. Are you enforcing it to not mask things that exist in the ground truth in the input, like in the MNIST Sudoku, there's 2 sevens. One of them was given through the input, the other was predicted. Are you trying to make sure that doesn't mask the input 7 and only the predicted 7?
Yeah, so for the first question, yeah, if the symbolic solver is differentiable, you can learn, like you can put everything together and then it would be even better. It's just the reality is most of the, because we want to use something that enforces the constraints, like hard constraints. So, and if you use some relaxation of logic or some differentiable solver, then usually it's not the case. So this is why we chose like pure symbolic solvers. And for the other question, so for the mass predictor, we basically generate synthetically because we know the rules, right? So with the rules, we can generate examples that violates the rules. So the mass predictor is trained on these examples. So you have some example that satisfy the rules, and then you can generate example that don't satisfy the rules. And you can generate as many examples you want because it's a synthetic data set on top of the rules. And so we train the mass predictor on that, and we ask the mass predictor to value more, so remove more things rather than less things. Because if we remove all the errors, then we are sure that the constraints are satisfied by the final prediction. Well, if we miss one error, then it doesn't work, right? Unless we are using probabilistic solver. But
Thank you. I thank again the speaker. Try to move the mouse. I don't know. No, okay, it works.
No, it works good.
Okay, so the second talk is a neural vector symbolic architecture for solving Raven's progressive matrices. So,
All right, I hope you can hear me. Hello, everybody. My name is Michael Herrsche. I'm a PhD student at ETH Zurich and IBM Research, also in Zurich. I'm presenting the work Neural Vector Symbolic Architecture for Solving Raven's Progressive Matrices. This was overall also a joint collaboration between ETH Zurich and IBM Research Zurich, and has recently been published at Nature Machine Intelligence. So in this work, we aim to solve visual abstract reasoning tasks in the form of Raven's progressive matrices. So you might all know this kind of IQ tests, maybe from job interviews or so. And the task is that we are giving context panels that are arranged in a 3x3 grid. And we need to find out what belongs to the empty panel at the bottom right by selecting one of the answer panels. And like those panels contain objects, whereby those objects are governed by underlying rules, mostly applied row-wise. So in this example, we see that the color stays constant per row, or that the number of objects at the rightmost panel is equal to the sum of the objects of the first 2 panels. So let's say 2 hexagon plus 1 pentagon is 3 squares. And by finding those underlying rules and applying them at the bottom row, we can infer like what kind of objects belong into the empty panel at the bottom right. In this case, it would be 4 hexagons which are shown at the bottom left in the answer panel set. And we approach this problem with neuro-symbolic architectures, whereby a neural network essentially recognizes the individual objects in the panels, and the symbolic AI infers the rule and executes the rule to predict what kind of objects belong into the empty panel at the bottom right. As we all know, this approach is very attractive, but we still inherit some of the limitations of the individual parts. On the neural network side, we face the binding problem, so we cannot properly bind information such as let's say color and shape and position properly together with the neural networks. And then on the symbolic AI side, we face expensive searches to essentially check all the possible rule realizations. And our approach to those problems is to introduce a meaningful vector space that is sandwiched between the neural network and the symbolic AI. In this vector space, that we call vector symbolic architectures, we represent concepts with high-dimensional random vectors. Because we are in high dimensionality, orders of 500s or thousands, and those vectors are drawn randomly, they are orthogonal with high probability. This concept is also known as quasi-orthogonality. On top of kind of meaningful vector, we also have meaningful operations to combine different vectors together. This is binding, bundling, unbinding, permutation, and inverse permutation. Overall, we call our approach neurovector symbolic architecture, and with that we can address the binding problem and also reduce the complexity in the symbolic AI by doing search in superposition. So let's have a closer look how we can approach the problem of solving Raven's progressive matrices with our NVSA architecture. So again, we are given our context panels, and we feed each of those context panels through, first through the NVSA front end, which does the perception. This NVSA front end essentially consists of a trainable neural network, which maps the input images to a high-dimensional representation, which we can then interpret with our VSA code books, and as output we get essentially confidences which objects are present, or we call them probability mass function, or PMFs. And then as a next step, as soon as we kind of recognize the individual objects, we do the reasoning in our NVSA backend. And there we first detect the rules and then execute the most probable rule. And because those searches can be quite expensive, we do it also in our vectorized space by mapping our PMFs to a high-dimensional representation. So I will first focus on the perception exclusively. So, and we look at the binding problem quickly, just as a short recap. So let's say we want to recognize different objects with certain attributes. So we have, let's say, attribute shape and attribute color. We can feed this image or panel through a neural network, which distinguishes between different colors and shapes, let's say red, blue, and square and triangle. And we simply we can train a neural network that we activate the red and the square logic. Same obviously holds also for a blue triangle. So far so good, but the problem becomes a bit serious if we have two objects that we want to recognize. So a red square and a blue triangle. If we pass them simultaneously through the neural network, it activates all of the logics. So now we have a kind of an assignment problem. So we don't know whether the square that we recognize has color red or blue. And we approach the binding problem, or address it, by learning nested structures with high-dimensional VSA representations. And this starts by defining the atomic concepts in terms of code books. So we have code books for all of the possible attributes. So we have color and the shapes. And for each of the attributes, we have as many code words as we have values of the individual attributes. So for the color, we have two attributes, red and blue. And each of those gets a high-dimensional representation that is a code word. Those high-dimensional vectors are shown with those QR codes, and they're again randomly drawn and high-dimensional, in our case 512. The individual elements are bipolar valued. And again, since we are working in high dimension and we randomly initialize those vectors, they're orthogonal with high probability. For representing combinations of attribute values, let's say a red square, we simply take the code word for red and the code word for square and bind them together using the Hadamard product. As an output, we get also a 512 dimensional vector. And the same can be done obviously also for the blue triangle. And since the red square and the blue triangle are orthogonal with high probability, we can also safely represent the red square and the blue triangle together using the superposition. So we simply add up those two vectors. Because they're orthogonal, we have low interference between those two vectors. So now we defined the target representation in our high-dimensional space, and we can simply train a neural network that maps those input images to the high-dimensional target representation. For doing the inference then, or like recognizing individual objects and attribute values, we can then search through all the possible attribute combinations or products. So it could be red square, red triangle, blue square, and blue triangle, right? And this kind of search space can grow quite quickly if you increase the number of code books or the values inside the code books by adding, for example, more colors. And this kind of large search space can be searched through with a so-called factorizer network. I will present this work in tomorrow's poster session, how to efficiently decode or factorize these representations using a factorizer network. So like going back to the actual Raven application, so we are using the iRaven dataset, and there we're working with 4 code books. We have 5 different types, 6 sizes, 10 colors, and 22 unique locations. And when generating all those bound symbols, we get overall 6,600 different bound symbols. And those are stored in terms of high-dimensional vectors in our W matrix. So for recognizing then those objects, we feed the images through a trainable ResNet-18. This gives us a high-dimensional representation where we can then compare this high-dimensional representation to all the possible bound symbols in terms of high-dimensional vectors. Hopefully, in this case, the similarity to the red square and the blue triangle is the highest among all of them. If not, we can train them with a novel additive cross-entropy loss by using the ground truth label. So in this case, we really know which objects are there in the training and during training. We have seen that this kind of loss works much better than, for example, a standard binary cross-entropy loss, where we are even not able to train the ResNet-18. So maybe just quickly taking a step back, with our approach, we are able to detect multiple objects by doing one single neural network pass. And this is not the case for other approaches. So what you normally do to address this kind of superposition catastrophe is to first detect the individual objects, for example, with a mask RCNN, and then classify the individual cropped images. This requires more network passes and overall also 6 times more parameters than our approach. So let's have a look at the classification accuracy for just recognizing the individual object. So we are not solving any Raven progressive matrices yet. Just in terms of how well our perception works, we show on the y-axis the perception accuracy, and on the x-axis different constellations. So the Raven dataset has like different constellations that showcase different difficulties. So for example, in the center constellation, we have just 1 object per panel. And in the extreme case, in the 3x3 grid, we have up to 9 objects per panel, which makes it more difficult for the perception and also for the reasoning later on. When looking at the state-of-the-art Neural-Symbolic approach, which is PRI, it achieves 85.3% accuracy. And with our approach, we get almost perfect accuracy with our new way of doing the perception. We can even reduce the number of training samples by a factor of 7 while still maintaining a high accuracy. So after we kind of, like one step we do in between is we map those cosine similarities to probability mass functions. And this is simply just doing some marginalization and looking that everything is non-negative and summing up to 1. And those PMFs are then sent to the NVSA backend, the reasoning. And what we do here is we do probabilistic abduction and execution. This means that we first compute for each of the possible attributes the rule probabilities. So we have a set of rules that we know, and we compute the rule probabilities given the first 2 rows. We then pick the most probable rule and execute it at the bottom row. And as an output of applying this rule, we essentially get, again, a probability mass function that shows kind of the distribution, the estimated distribution of the empty panel at the bottom right. And we can then compare this distribution against all the possible answers and select the one with lowest distance in terms of divergence. So like all those blocks are of high importance, but what we have seen is that especially rule probability computation can become a bottleneck computationally. So in the standard symbolic approach, I will give an example for the arithmetic plus rule. So in this case, again on the number, so the number of objects at the rightmost panel is equal to the sum of the first two panels, so 2 plus 1 equals 3. And what we get as input are PMFs. So we have some certainty that maybe in the first panel there are 2 objects, but it could also be that there are just 1 or 3 even. And for computing the probability that the arithmetic plus rule is present, we set up a truth table and go through the truth table and sum up all. And for all the valid combinations, we multiply all the probabilities and sum all the valid combinations together. And then we might end up with a statement like arithmetic plus is present with a probability of 0.7. This table can become quite large in some of the cases, especially for the distribute tree rule when you're working with the position attribute. So there we can have up to 511 different position scenarios. So our PMFs are 511 dimensional, and overall we need to search through 26 times 10 to the 7 rule realizations. And that's a bit too much for the symbolic search. So what the state-of-the-art Neural-Symbolic approach did, they limited the search space to being able to cope with this large search space, which ended up in lower accuracy. And what we do in our case is we compute those rule probabilities by performing the search in superposition. So what we do is we first map those PMFs to a meaningful high-dimensional representation. And then we can simply implement the rule by applying single vector operations. In this case, it's just the vector binding of the first 2 panels for implementing the arithmetic plus rule. And then we just do one single vector comparison. And then we would also end up with some statement like arithmetic plus is present with probability 0.7. Maybe like just quickly go a bit more formally through the steps. So what we do is, again, we set up code books. In this case, we use a bit different representation. So here we make use of binary sparse block codes in combination with fractional power encoding. This basis essentially just guarantees that we can encode relations between different PMF values. That kind of 1 plus 2 equals 3 also. And then we transform those PMFs to our high-dimensional representation. This is just a weighted superposition where the weights are the probabilities and essentially the basis vectors are used for doing the weighted superposition. And we then do the rule application. As I have shown before, we bind the first 2 panels for each of the row, and then we compute the rule probability by doing 2 similarity computations for each of the row. And if then the rule is the most probable one, we would simply apply it also in the vector space by just binding the lowest 2 panels, or the vector representation of those panels. And then finally we can transform it back to the PMF space. And this way we can do the search and superposition while still staying transparent. So in all of the cases, we can always do similarity computations between our vector representation and the basis to get back to the PMF space. This makes it transparent and also much more efficient overall. So here I show just results of the pure backend. So we just do the reasoning. We provide the ground truth labels or attributes to the NVSA backend. And we show the reasoning accuracy and also the compute time on a CPU. We had to do it on a CPU because of space The PRE achieves an accuracy of 94%, so not 100%, because it has to limit the search space, which yields lower accuracy. We then played a bit around with the PRIE, the state-of-the-art neural-symbolic approach, by relaxing those constraints, but it yielded us requiring 10.7 days for solving 2,000 Raven progressive matrix puzzles. And with our NVSA, we can maintain that high accuracy, but reduce the compute time by 2 orders of magnitude. So far, I discussed the NVSA front end and the back end in isolation. So now it's time to plug them together and train them end to end. And we can train this architecture end to end by applying a reinforced loss at the output, where we compare essentially the distribution that we predicted and the correct answer panel, plus a additional auxiliary loss where we also can use the ground truth rules that are applied for the different attributes. And overall, we just train our trainable ResNet 18. All the VSA code books are initialized at random at the beginning, but fixed during the training or frozen. So let's have a look at the overall accuracy on the iRaven dataset. Again, on the y-axis, I show the accuracy for solving the entire test. And then on the x-axis, I show again the different constellation with different difficulties. On the very right, we can see the average accuracy. So we first look at the classification accuracy for the state-of-the-art neural-symbolic approach, which achieves 71.1% on average. We also considered the state-of-the-art deep neural network, which is actually better than the neural-symbolic approach in this case, achieving 84%. And with our approach, we outperform both the neural-symbolic and the deep neural network approach by achieving 88% on average. We also tested or explored a bit the generalization capabilities of our architecture. So first we looked at the generalization of the NVSA frontend, again in isolation. And what we have been interested in was, can we recognize certain attribute combinations which have not been exposed during the training. So in this case, we show, for example, all the objects of color white, all the types of color white, and all the colors just of the shape triangle. So what we kind of were asking, for example, was, can we recognize a black hexagon when we just have seen a white hexagon and a black triangle? And the answer is, with the pure multiplicative encoding, it's quite challenging, so we didn't see that much of generalization in this case. But we also played around with a bit alternative high-dimensional encoding, where we do key value superposition. So we essentially have a key for each of the attribute, let's say for type, color, and position and size, and then we have the value, which is another vector. We can bind them together and also superimpose it, all of them. And together with a sophisticated hyperspherical prototype loss, we are able to achieve generalization up to 72%. This is just for perception. What we also have been interested in was that whether we can also generalize towards never seen attribute rule combinations. So in this case, it's again now end-to-end results. We provided all the possible training samples with all the possible rule attribute combinations, except in this case for the type and the progression. So there was not shown any example where the type progression rule was applied. And we generalize much better than all the baselines in this case, achieving in most cases even 100% accuracy. So to sum up, we propose a neural vector symbolic architecture that sets the new state of the art for solving Raven's progressive matrices. And we achieve it by representing structures by using a conceptual space. And we do abductive reasoning with distributed representation, which is 2 orders of magnitude faster than doing a pure brute force search. And we also maintain the transparency, which is very important. Our architecture can be trained end-to-end we achieve a new accuracy record, and we see some degrees of generalization in our approach. You can see, or you can ask then also more questions in the poster session after the coffee break. And if you're as excited about VSA as we are, you can also check out yet another poster that we present, where we apply the VSAs not only in the kind of object space or spatial relations, but also time relations, where we do positional encoding in emergent symbol binding networks. Our code is also available, so feel free to use it and give us feedback. And with that, I want to thank you for your attention, and I'm open for questions.
Thank you very much. Nice talk. Danny Silver from Canada. If I got it right, you selected the code shapes. Is that correct?
Yes. Yeah.
Have you? Because they're effectively embeddings, right?
Sorry, can you repeat? I'm fully.
Have you considered learning the code books for the colors and shapes?
In the visual perception, we tried to learn it, and it didn't give us improvement. But it's also a bit tricky because our binding is the Hadamard product, and when we start to learn, when we start from bipolar representation and learn things, and things can end up with 0. That was a bit tricky.
Okay, we can talk after.
Yeah, that's good. Yeah, perfect.
Hello, I wonder whether if the image contains two figures which are both red but of different shape. Okay.
Yes, that's no problem at all, because let me just quickly show again. Okay. All right. So essentially, when binding is essentially orthogonality preserving, let's say. So if I bind red with square or red with triangle, because the square and the triangle are orthogonal, also their bound representation will be orthogonal.
Hi, nice talk. I'm new to the domain, so maybe this question is a bit naive, but is there a question to choose this type of representation instead of performing image segmentation and trying to then take all the shapes one by one?
Yes, yeah. You can do that as well, yeah. That's what I show essentially here. This would be an alternative approach. With our approach, we just need to do one network pass for recognizing all the objects. That's kind of the key selling point.
Referring to your previous slide that you were just showing,
this one, or
the one about the representation. I think later you mentioned at some point the positional VSA code book, but are you applying, so the red box, if it was on the right, would have a different?
Yes, yeah. We also, this is just half of the truth, right? It's just for illustration. We also have a code book for the position. And there it also gets, like, also in terms of generalization, and we have seen that it can, like, so far it's quite tricky to see generalization then in the, like, obviously you can train your network that it's robust against some shifts, but it's possible to represent also the positions with binding it there. So essentially a red square on the left is orthogonal to a red square on the right there, because the positional encoding is also orthogonal.
Any more questions? I have one quick question about the task, because how many rules you are using for this task, and is it required to generalize also at the rule level? So are there rules that you don't see during training?
Yes, exactly. So that's what I essentially showed at the very end about the rule generalization. That's just one experiment that we set up, where you just don't see the progression rules for some of the cases. You could also just leave out some of the rules entirely. Let's say just don't show constant, but thanks to our symbolic approach, we can still program it right. But it's then up to the front end to be able to learn everything, to show like sufficient kind of variety of examples that it can learn the representation. Yeah, but overall we have the rules constant, progression, distribute tree, arithmetic, and yeah, the individual rules have then also multiple instantiations, but yeah, that's essentially it.
Thank you.
I will go first. Just plug it in as fast as possible. It takes some time.
HDMI or something?
Yeah, there's HDMI. This one, yeah.
Yeah, I have my own. Thank you.
So it's a bit slow. Oh, okay.
Coming, I think.
Let's try to move the mouse in the meantime. It's unclear to me how this works.
I'm gonna try this one.
Yeah, try that one was working before. So. Otherwise, you have just a PDF, you can transfer it here. Let's see.
PowerPoint. Sorry?
Ah.
Okay.
It's very.
Let's hope it stays.
Yeah, usually it stays after it's
That's a
flickering
good
a little bit, but then it's okay. So I welcome the last speaker of the session. So, what's wrong with gradient-based complex query answering?
Thank you for the introduction. So this is a work that we did at Sony AI with one of our interns, Uns. Unfortunately, he couldn't be here this time, but he's hoping to come next year at the NeSy conference. And as Tarek commented, it's kind of funny that he looks the most formal out of the three of us. But yeah. So a bit of context. What do we mean by a complex query? When we talk about a complex query, essentially we mean a multi-hop query that has some logical constraints over a knowledge graph. So we give an example here of a simple two-hop query, which is which drugs interact with a protein associated with the cancer disease A. And there's several ways of visualizing that, either through natural language, as I stated it. Then also we have the visual representation that I'm going to use throughout the presentation with the space of drugs, proteins, and diseases. And finally, the equivalent first-order logic formulation, which I think we are in a symbolic crowd, so everyone understands it. But when I present it at my office, it's not always the case. And we specify a bit the task of answering complex queries over knowledge graphs by some state-of-the-art methods. They use data sets of complex queries and answers to learn a model that can answer such queries. We don't want to do that because often in real-world scenarios, we don't have such data set of complex queries and answers. Instead, we're just using pre-trained embedding representations that have been learned on the knowledge graph. This is very easy to do. And link predictors, there's also many models to do that without relying on any additional new data. So this is not completely new work. Basically, we're building up on work from the group of Amsterdam, done by Arakelian and Al in 2020, who proposed what's called complex query decomposition, which is a method to compute the satisfaction level of answering a query for any points that you take in your knowledge graph. So those points have embeddings and so on. And essentially, it's using first-order fuzzy logic to estimate this fuzzy satisfaction level. And it's a two-step process. First, you take the neural predictors, given your embeddings for your concepts and your relation, and you compute an atomic truth degree for each of your atomic links in the queries. And then you compute complex fuzzy satisfaction value using fuzzy t-norms or t-conorms, depending on how your query looks like. And what's important here is that this is a continuous function from the space of node embeddings to the space of satisfaction values between 0 and 1. And we're going to use the fact that it's a continuous function to basically propagate derivatives and help finding answers. But so yeah, essentially with complex query decomposition, we have a way, given any embeddings, any feature points, to estimate their satisfaction level. But we cannot test all the combinations of points in your knowledge graph if you have a large knowledge graph, because there is a complexity that's exponential in the number of hops in your query. It's just not feasible to test all of them. So Arakelian and Al proposed two search algorithms as solution. The first one is essentially a beam search. We're not going to work with that in this presentation. But the other one that we're most interested in is a continuous optimization method that's going to learn to search for good answers. And the second one doesn't work as well as the first one, and that's why we tried to improve it. So describing this method in more details, is the GIF working? Nice. Basically, we have two variables in our query. Like the disease is fixed. We are trying to find things that relate to cancer. But the protein and the drugs, it can be any points. So what we try to do is to search those points by, we fix the neural link predictors, but what we don't fix is like the feature representation of the variable points. And we learn what are going to be the points that maximize the satisfaction of the query. However, it's important to note that this is in the feature space. So at the end, you're going to get some points that are going to be like a vector of continuous values, but they don't correspond to any real data point. It's anything that's found in this feature space. And when you want to answer the query, you need a real data point. So after this phase of learning the features, you need to actually test the real knowledge graph nodes using what you have learned. And the way they do that is that they fix the intermediate nodes in your, the intermediate hops in your queries with the representations that they have learned. That don't correspond to anything, but it's not a problem. We're not looking for what's the protein, we're looking for what's the drug. And they test the real drugs with those non-concrete representations that have learned. But here they can test all the drugs because we don't have the exponential complexity anymore. You don't need to test with all the proteins. You just have your representation that you have learned at the previous step. So there's no complexity problem anymore. So it's really nice, but one comment we have is that there's an obvious limitation, is that here you're fixing this node and you're testing all the drugs against this thing that corresponds to somewhat a protein. And if you look back at the examples we have here, often in knowledge graphs, you have different possible paths that lead to your answer. You don't have like one protein that's going to respond to all the drugs. You might have other drugs that use different proteins. So our first contribution, it's really intuitive, is simply to try to learn several of those intermediate nodes, and we call them like answer paths. And we learn P of them, so there's this hyperparameter P that we're using that's gonna describe how much exploration we leave, how many answer paths we explore in parallel. And then we still need to do the test step and to adapt it. And this time, instead of testing every drug target with one protein, you need to decide which intermediate node you're going to test it with. You could test them with each of the intermediate nodes that you have, but then we're trying to be efficient, so we don't want to multiply the complexity. So what we decide to do instead is to take the answer path that has the nearest neighbor in the drug space and to test against this answer path or real drugs. And so the hypothesis here is that if we learn good embedding representations during the pre-training, we assuming that they should be somewhat clustered by similarity, and that we can say, for example, that if this V2 fit this T2 node, it should also fit its local neighbors. So that's the assumption we're doing. And so, yeah, that's a small improvement on the method, but there's still, you have still a fixed number of paths, which is this P hyperparameter. And we're thinking, okay, how can we have something that's not fixed? We can explore as many paths as we want without increasing complexity. And so what we thought about is to use scolem functions. So essentially, this proposition is like, you learn functions that project from each hop to the next using a neural network. And so now you don't have any fixed points anymore. You have a fixed neural network, but this fixed neural network can project to any new point given any new drugs. And we learned this neural network using P examples still, but this P, when we do the test phase, it's not used anymore. Like, all the drugs are going to have their own projections. It's like, there's no jealousies. Everyone has the same chance to be an answer, let's say. And in theory, I really love this idea. Unfortunately, it didn't work. So we have those three methods that we compare the results. So the CQDCO, the work from Amsterdam, CQDCO multi that use the multiple answer paths and the nearest neighbor approximation, and then CQDO scolem. So by the way, scolem, it's because technically the fact of projecting from one node to the next, replacing your existential with a function is called a scolem function in first-order logic, but I mean, it's just for formalism. And so yeah, we tested this. So this is early work, by the way. This is still, we're trying to improve this. And we measured the three methods using the hits at 3 scores over 2 hop queries over the Freebase 15K dataset. And so some things to say about the hyperparameters. Of course, there's the P, which is like the number of answer paths in the multi approach and then the scolem approach. And then you also have the batch size parameter. So you're not going to do learning query by query. It takes too much time. But you can basically batch them and do learning for many queries at the same time. And so it's efficient. And one small thing to notice already is that you need to trade off between the number of, the higher your P is, the smaller you need your batch of queries to be. Otherwise, we just find that it's too hard to learn everything in parallel. And yeah, some early comments. As I said, the scolem projection doesn't work. Like 2% hits at 3. It's not what we hoped for. But we have, so essentially, it doesn't work because we're trying to do a regression with something like max 100 examples from one highly dimensional space to another. It's not really doable. So now we're exploring other alternatives that's using classification instead of regression. But here, the main takeaways we have in this paper is about our analysis on a CQDCO multi. It performs better, but almost the same as the normal method. And we were wondering, like, why is it? It's only 1 or 2% difference. We were expecting something more drastic, either better or worse, but it's almost the same, and we're wondering why that is. And so when Un started to analyze the results, he found that the regularization is really limiting the exploration. And so we noticed this by working with CQDCO multi, but actually the same problem also happened with the normal CQDCO. It's just that it's more hidden. But what happens is that we are expecting to find like diverse answer paths and so on, but because of the regularization, they seem to all be constrained close to the origin. So you have all those points that are gathered, and then your local neighborhood assumption is not useful anymore because they're already in the same local neighborhood assumption. And so the regularization that was used in previous work was canonical tensor decomposition, which is basically coming from the complex paper, if you know, for knowledge graph completion. And it's very complicated, and we try to have different weights of regularization. And it was either turning it completely off or on. And it was really hard to work with it. And then we tried a simple L2 regularization, and then it just had the same results. And we're like, why do something so complicated if the simple solution works as well? So now we are basically saying, like, keep it simple, you know what's after. And we just trying to work with the L2 regularization and have more like, let's say, control on it. Then the second limitation we found is that there is a strong bias in your neural link predictors that have been pre-trained beforehand. And so there are 3 subpoints. The first one is really easy to understand, is that if the predictors learn something wrong, we don't change them through the query answering, so there's no way to escape that. So it means that often what we found is that the top 1 prediction of the complex query answering method had a better satisfaction than the ground truth prediction in 40% of the case for CQDCO or 45% of the case for CQDCO multi. So that's the SAT metric that we say. It's like, according to the confidence of the link predictors, this is a better answer, but it's impossible for your answering mechanism to, with how it is designed now, to escape that. The other 2 points are a little bit more hidden, is the fact that the distribution of the link prediction scores were skewed in very small regions of the interval 0, 1. So it means that a wrong and correct answer, sometimes correct answer is going to be like a higher scored satisfaction than your wrong answer, but the gap is going to be really small, like 0.01. And that's because those link predictors were not made to actually represent fuzzy truth degrees or probabilities or whatever you call it. They were more made to just like the argmax be the correct answer. And so this is very difficult to alleviate when you have a continuous method to discriminate between the 2 if they're all skewed in the same region. In comparison, the beam search method, because it's discrete, is also just taking the argmax, and so it doesn't suffer from this problem. So we thought that's pretty interesting. And I have to say, after we finished this work, we found out that the Amsterdam group did a new work that's now on archive, and I've heard during this conference that it's in submission to a conference, where they learn to recalibrate the predictors basically to solve this issue. But the way they do it is using now they use a data set of query answer pairs to recalibrate the predictors. And we are still on our side exploring ways to do that doesn't require new data. And we're just thinking like to even out somehow the output distribution of your link predictors using heuristics and so on. If you want it to be bimodal or logistic or something, you can try different things. Or to bias the pre-training loss function to make sure that it's also well distributed over your space of 0, 1. And that's pretty much it. So it's early work. We have some recommendations if people are also studying this question, which is 1, then change the regularization technique. 2, improve your link predictors models, calibrate them and so on. And 3, explore better models for Skolen projections. But this is more of really new work. And yeah, I would really like, if you have time during the poster session, and if you have some ideas actually for the regularization technique, this is where we are a bit more stuck. Would really be useful to have some of your inputs. And thank you for attention. Yeah.
Questions?
Thank you, Sami. Thanks very much. Can you go back to the multi-hop, the nice picture you have with the multi-hop there? Just a general question about why you feel, having done this work, why it continues to be such a difficult task, even 2 hops, right? And shouldn't it just be reasoning? If you come from a symbolic logic background, you wouldn't even discuss how many hops. It's just reasoning, right? So it's, do you think this has to do, you hint at the regularization, which is interesting. So I think in one of yesterday's talks, Jan Lecan was arguing for more regularization. I was just trying to connect this, and just a general question as to why you feel it's so difficult to solve the multi-hop problem.
Yeah, thank you for your question. I will also refer to Jan Lecan's presentation yesterday. When he was explaining about the natural language, when you're completing a sentence and you have this, the more you proceed step by step, the more you have an exponential risk of making a mistake. And I think you have a somewhat similar problem with the hops. It's like at each hop, you have more risk of making a mistake. And you kind of need to like keep your top results of the previous hop and just explore those. And so if you're a mistake in the stop, then you're basically, all the leftovers hops are screwed, let's say. And about the regularization, I think regularization is really important, but in this case, it just needs a better regularization. It's just that the regularization was just constraining to be close to the origin, and not really. We need almost a regularization that comes from generative models that makes sure that your points is like similar to other points, but not specifically close to not specifically work on the norm or like the distance to the origin.
Yeah. Other questions? I wanted to ask you something otherwise, but why all this focus on regularization or not? You know, there are ways, right, to regularize your models, like a dropout or many other things. Why all this focus on regularization?
Because if you don't put regularization, what happens is, so the problem with regularization was that the points were all clustered together. But if you don't put regularization, what can happen is your point, instead of being somewhere in this slide, is just, it was really too far out of the of the real points. And in this case, when you're doing complex query answering, you need your points to correspond to real data. And dropout, it's gonna make sure you don't overfit, but it's not gonna make sure that you stay close to data. So no.
Yeah, I mean, that's the trade, right? That is
Sorry?
No, okay. No. Sorry. I mean, of course, then you have the trading that is making you staying close to the data as well, right? So.
Yeah, actually, I didn't dig in that much in the objective function, but so I'm just taking the simpler example. The training is just making sure that you maximize the satisfaction, but in itself, there is nothing that says that it's close to the data or not. Your features can be, they could take a shortcut and just go like in a region of the search space that's for some reason has not been explored during the training of your link predictors, but that's giving you a high result. And it can, this is a new training process that can exploit the fact that the previous link predictor didn't explore everything. So yeah. Thank you.
Any other questions?
Thank you. Thank you for the presentation. Just a curiosity about what you just said. Perhaps I missed it. In this gradient descent that you apply here, So what is the starting point of the optimization? Because I think the result will be strongly biased by this. Also, your comment about going in some space regions in which there are no evidences might be because of that. So where do you start the optimization?
Yeah, it's a great point. No, we just randomly initialized the same way that was done before. So somewhere in your feature space, but we didn't really try to skew the initialization, and no, it's a great idea. We should investigate that.
Okay, more questions?
So I have a follow-up to the answer you gave to Arthur. You mentioned that you can get good regularization using generative models. I was wondering where you were coming from. Can you just quickly elaborate on that?
Yeah, so actually it's something I would like to talk about in the poster because I'm not from a generative model background, but my intuition is that there's a lot of overlap because why we want to regularize here is to have points that corresponds to real points. And I'm wondering if there's a way, instead of doing that through L2 norm or whatever, to do that through somehow you incorporate a VAE in your system to make sure that it corresponds to a real point and not to something random. But yeah, it's open for discussion. I don't have a clear idea how to do that. Yeah.
More questions? Okay, otherwise I thank our last speaker, and yeah, this is concluding the session. Thank you.
Yeah. Okay. Good morning, everyone. My name is Lia Morra, and I'm going to present an exploration of the task of visual Sudoku puzzle classification. This work started within the context of a sort of mini challenge that we organized in a PhD course on neural-symbolic artificial intelligence that I organized at Politecnico di Torino, which is my institution. This task is slightly different from what we have seen today, since we are given a Sudoku board that may or may not be correct, and we need to understand whether the board is correct without having access to the individual digit classification labels. So we are using a neural symbolic component to encode the rules of Sudoku and backpropagate the error to the actual digit classification. My goal today is not necessarily to convince you that LTN is the best framework, although we do beat the previous baseline. So if you're interested, please come to see the results. But really to understand with you if these tasks can be used to provide some guidelines for a number of engineering problems that arise when we moved from traditional deep learning to neural symbolic integration, and in particular, the need to address a number of design choices and a number of additional hyperparameters that were not present in the original network. Also considering that many of the practitioners that come from a data science or a machine learning background do not have a formal training in formal logic and are kind of a newcomer to this field. So please come to our poster and help us solve this problem.
Thank you. For the record, that was 1 minute 45 sharp. You find me impressed. Okay, you're good to go?
Yeah.
Go.
Hi, everyone. My name is Roxana, and I will quickly introduce our short paper. Next. I assume all of you are familiar with knowledge graphs. What I'm interested in is temporal knowledge graphs, where each of the facts can be annotated with time points or time intervals when they are true. Now, there's different tasks we can do on this type of data when in a learning setting. I'm focusing on time prediction. And also for time prediction, we can consider many different settings, and I will not bore you with those now. I can do it at a poster. But basically, it's not an easy thing to define, and our first contribution in this paper is to formalize a learning task on this type of data, that of inductive future time prediction on interval-based temporal knowledge graphs. Okay, I think that was it. We also introduced a Neural-Symbolic approach. We started drafting something, and the main idea is to extract a set of temporal logical rules in data log MTL from a trained neural network that is trained on the task. And we can discuss more about it at my poster. Hope to see you there. Thank you so much.
I'm actually speaking tomorrow, and I didn't realize that actually I had also the possibility of presenting a poster, so I don't have anything, so come tomorrow. The idea of this paper is to describe, from an industry perspective, what are the challenges to try to apply neurosymbolic methods to robotics applications. So the OODA loop that you see there in acronym is observe, orient, decide, and act. Is very, very similar to what Jan LeCun yesterday spoke. But it's a more engineering perspective of that. And so I would like tomorrow to hear from you guys, from academia, and what the current research is heading towards, if some of these challenges that we perceive in industry are real, or there are some tricks that we can apply, or maybe even inspire academia to channel the efforts towards these challenges. So come tomorrow to the industry session.
Okay. Go.
Hi everyone, so my name is Arthur, and with my co-authors we wrote a small position paper with some insights on how to improve maybe the benchmarking of Neural-Symbolic AI. Next. So we focused on a very particular task, but we believe that those insights can be actually generalized to many tasks in Neural-Symbolic AI. And so the task is a binary classification task where we have a propositional formula on the output space that kind of expresses what are the valid labels and the invalid labels. Next. And so the first thing that we observed was the distribution of data sets on that task. So we identified different design patterns for the data sets, and we observed that there was a huge missing area for high symbolic and sub-symbolic complexity data sets. And so the ROD-R data set is trying to fill that void, but I think there are more efforts needed in that area. And next. And so the second insight that we had was on control metrics. So the idea is to control the capacity or resources given to the model. And next, this is important because the two previous result experiments may seem similar in the sense that NeSy outperforms the purely neural baseline. But if you take into account the dynamics of both accuracy curves with the capacity of the model, you have very different answers to like
questions like how can we compress the size of the model using NeSy techniques and so on. So come to the poster to discuss more these questions.
Go.
Yeah. Why do we need physical world models for robot learning? Next. So machine learning has shown great success for robotics applications. However, large amounts of data were needed, for example, 800,000 attempts for learning to grasp, or 10 years of simulated experience to learn how to manipulate a Rubik's Cube with only a 20% success rate. So we usually end up with uninterpretable models that are hard to train and do not generalize well to new tasks. Next. Our position paper suggests the following approach. Given a prior distribution for the parameters of our graphical model, we can have a single image, a photo of the environment, to use inverse rendering and Markov chain Monte Carlo to arrive at a representation of the scene. Next. With this Bayesian approach, we have an inherent uncertainty quantification that we can use for the robot, which has a camera mounted on its wrist, to obtain a second image of the scene to minimize the model's uncertainty. And then, next, we extend this with dynamics to have a hybrid differentiable simulation in which the complexity of the model physics is adaptable to the task requirements. Again, we use the uncertainty to generate exploration behaviors like poking or pushing an object to generate trajectories that we can use to estimate a friction model. Next. This is a fully differentiable model that can be used for optimal control or classical deep reinforcement learning to achieve task-specific behaviors.
Thank you. Go.
Hello, everyone. So I'm presenting here and at the poster session a work about solving simple arithmetic problems with a hybrid system. Next. So I would like to start by asking you, how would you solve this expression? Or next, this one, or next, this one. Next, probably what you will do is to derive the solution in an iterative fashion because you don't look at the expression and immediately realize what's its value. What we are proposing next is exactly a hybrid system that does this kind of computation. So our hybrid system has a text-based neural trainable component which receives the full expression and outputs the value of its innermost sub-expression. And then next passes this to a deterministic, let's say, algorithmic component, which substitutes the proposed solution of the sub-expression in the original expression. Next. Then the two are pipelined and executed iteratively to solve the full expression. Next. So the two main results we have is that the first component, which is trained on very simple expressions, can generalize to more complex expressions thanks to some particular kind of positional encodings we use. Next. And the full system can generalize to complex samples much better than end-to-end trained alternatives, including a version of GPT 3.5. If you're curious about this, come see me at the poster.
Go.
Okay, thanks. So my name is Francesco. Today I will be presenting some work on how to use VSA or vector symbolic architectures to do time encoding. So I guess most of us here are familiar with LSTMs, so long short-term memory. And most people who use LSTMs end up hating LSTMs because of how obnoxious they are to train, to do inference, how bad they are in general. So wouldn't it be cool to get rid of LSTMs entirely? This is what I am proposing here, to use VSA in sort of a more fancy way using fractional power encoding. And if you want to know what all of these big words mean, come to see me at the poster, to replace LSTMs in a emergent symbolic binding network with the final task of doing variable binding. And that's it for my side. So come see me at the poster.
Nice. And go.
Good morning, I'm David Heron. Next. When you're doing NeSy research using owl-based knowledge graphs, it feels like AI can be given a cartoon characterization such as this, where owl-based knowledge graphs are interesting curiosities perhaps, but aren't getting an awful lot of attention, and that's backed up by the literature. And it's curious and interesting because once you begin to realize and appreciate the capabilities of owl-based knowledge graphs, next, it feels like a relationship, a more collaborative relationship such as this one would be appropriate, where the potential for leveraging the capabilities of owl-based knowledge graphs is being more fully explored by the community. And so we want to promote and encourage this transition in state. And we can do that in a couple of ways. Next. First of all, we want to inspire. We want to inspire more NeSy research using owl-based knowledge graphs by raising awareness of their benefits, their capabilities, and their applications, especially with respect to deductive reasoning and agency, which are the real uniques of owl-based knowledge graphs. And that's what our position paper is all about. And next. And the second thing we want to do is enable, because to do research in this space, you need a specialized kind of resource, the kind of resource that's quite scarce.
10 seconds.
And you need a resource like our NeSy for VRD, which we recently contributed to the community. It's an image data set for visual relationship detection, and it has a strongly aligned companion owl ontology ready-made to allow exploration of knowledge graph, owl, and data log reasoning. So, to be inspired by and enabled with owl-based knowledge graphs, check out our poster. Thank you.
And go.
Hi, my name is Katrin. I'm presenting the paper called Causality Prediction with Neural-Symbolic AI, a case study in smart grids. There we tried to use sub-symbolic AI to improve a knowledge graph that was created using just purely symbolic solutions. Next. Our system that I'm talking about is a smart grid in an energy village, and there you have some events that need to be explained. For example, an overload in a transformer or an e-car charging that is super slow. Next, please. Here you can see the symbolic solution that we already had before. So you have a knowledge graph which is created through different steps. So we take the system data directly to create the topology, and there is an event detection process as well as some causality derivation for the sensors as well as the events. So this is purely symbolic. And then in the next slide, we use the sub-symbolic extension to where we train the knowledge graph embedding on the knowledge graph that we already had, and use link prediction for the causalities to ideally improve the knowledge graph and the causality relations that were already there. Because, yeah. And then our results were quite promising, which I'm happy to discuss in the poster session. Thank you.
Go.
Hello, my name is Manuel, and I'm presenting the paper towards explainable decision-making with neural program synthesis and library learning. And while I was working on more domains for a conference submission, I unfortunately found a bug, but luckily before the submission, and now the results change a bit, but the content is the same. And next slide, please. Now I changed the title to Learning of Generalizable and Interpretable Knowledge in Grid-Based Reinforcement Learning Environments. which is also like the core of the paper. And next slide, please. And our motivation is that it is crucial to understand the interactions of agents trained with deep reinforcement learning before deploying them in the real world. And therefore, we propose to use program synthesis with library learning to imitate state action sequences of the policy. And next slide. And yeah, therefore, we adapted the state-of-the-art program synthesis system Dreamcoder and integrated it to work with reinforcement learning environments and integrated it with a curriculum. And we also exchanged the symbolic-based program synthesizer with a neural program synthesizer and compared the libraries of both program synthesizers. And next slide, please. And here we can see on the left a program without library learning, and in the last line is the same program when we use library learning. And on the right are the generated explanations when we traverse the program call graph of the synthesized program. Yeah, and if you're interested in program synthesis, check out my poster later. Yeah.
Thank you. Go.
Hello, so my name is Alessio. So this work carried out at Imperial College London. So at Imperial, we've been looking at AI safety issues for a good 20 years. And particularly, we look at formal verification as one of the ways to ensure the systems are safe. And next slide, please, Tarek. So we've been looking.
I did not receive slides.
Oh, okay. Okay, that's okay. So we'll be looking at verifying systems, typically autonomous systems that are normally symbolically programmed. So they have a program and you verify through techniques such as model checking, fear improving, and so on. Now in this work, we look at neural-symbolic systems. These have a perception layer together with the symbolic action selection layer. So perception is governed by neural networks such as Siena and so on, and then we have decision making which is entirely symbolic or programmed. So we formally verify these systems and we give guarantees, both formal and through implementations, in terms of how to verify these systems. So the bad news is that in principle this is undecidable. But in practice, if you take a bounded fragment of these systems, you can prove some complexity bounds for their formal verification. Now, technically, the problem becomes an optimization problem formulated in mixed integer linear programming. So we also build a tool which we presented at KR 2020, through which we can verify neural-symbolic multi-agent systems. And we verify them against temporal logic, but also from the title of the talk, you see that we verify them against strategic specifications. So things like what can a bunch of agents can achieve during a run. And so in terms of application, we looked at advisory systems in aviation, and I'll have more details in the slides in the poster session. Thank you.
So this work is in the context of safe reinforcement learning, which is like training an agent to achieve a goal while staying safe. Now, and the standard approach, this is shielding. So if you look at this image, shielding is in the standard interface agent environment. The agent is like, takes an action, but there is a shield that says, is this action safe? Is yes, then you can apply this action on the wall. Otherwise, you go back and you give the control to the agent, pick another agent. And there are a lot of problems with this approach. Usually, it's in the standard symbolic formal verification setting, and so something is either safe or unsafe. You need perfect knowledge of the model. It's inefficient, and for us, in the Neural-Symbolic, it's not differentiable. So what we did, please, next slide, here's to pick the same shield and substitute it with a probabilistic logic shield, which is a probabilistic logic program. So by doing this and keeping the entire framework exactly the same, we have now the possibility of defining probabilistic safety. We can handle uncertain scenarios, so we can have also neural networks, neural policies, and we can infer using tractable probabilistic inference, and everything is end-to-end differentiable, so we can use out-of-the-shelf arguments for this. So if you're interested on how that works, come see me at the poster. Thank you.
and go.
Hello, everyone. I'm Dajan Kwagu, and I'll be talking about neural class expression synthesis. Next, please. Did you know that class expression learning and description logics can be used for explainable node classification on RDF knowledge graphs like this? Well, that's the case. Next, please. Let's assume we have two sets of examples, the positive ones which are green and the negative ones which are red. And we would like to compute an expression that describes the positive examples but not the negative examples. Next, please. Well, example solutions could look like this, or, next please, or like this. But how was this tackled in the past? Next, please. Oh, yeah. And regarding the readability and explainability of these solutions, we are happy. Next, please. How was this tackled in the past? Like I was saying, it was via search. And what's wrong with this? Next, please. It's expensive. And can we do anything about it? Next, please. Yes, and the solution is NCS, Neural Class Expression Synthesis. If you are curious about our approach, please come to the poster. Thank you.
Thank you. This was 13 pitches. The 3 spotlight papers also have the opportunity to be presented as posters. So if you still have questions to those, presumably these people will also be around. And otherwise, we resume at 11:30. Or rather, the poster session starts at 11:30. Thank you all. Very well done.